So James got his bachelor's in astrophysics from Princeton, and then went off to Cornell for his grad school in astronomy with great Steve Squires. And then he was one of those people that I really looked up to because he got his grad school, his PhD in 4 years, and right after graduating had a tenure track position lined up for him. And so I met James when he was still doing this small postdoc, and he convinced me to come to Georgia Tech as a grad student, and so I'm very glad that I did. So any of you taking classes with me in remote sensing or anything, so he's the OG remote sensor that got me into this mad world. So James has been there for almost 13 years now, and in his free time, he's also like an ultra marathon runner now. So there's a lot of different sides to James. Very happy here. I'll let you take it away.
Well, thank you very much, Luzu and Ben and everyone for inviting me here. Do I sound okay? Right there? Great. So I asked Luzu in the last couple of weeks, do you think folks would want to hear about Mars, or which is what I've done most of my planetary science on, or lately I've been thinking a lot, getting excited about interstellar objects. Do you think they'd want to hear about that? And his answer was kind of, how about both? And I thought, okay, great, but what can I use for a title that would link these two things together? And I thought about it for a few days. I couldn't come up with anything. And then one morning, I stumbled out of bed into our master bathroom and found this sippy cup of milk in our bathtub. And my reaction, of course, was, well, how did this get here? And I know the answer because we have a not yet 2-year-old, so he's clearly the answer for it. But then I thought, that's it. That's the theme to the various scientific investigations I've sort of focused on in recent years and that I wanted to tell you all about today. So the toddler's reorganization of the house makes me ask that question a lot day to day. I also turned 40 just a couple months ago, and so it's a time when you start to think, like, how did I get to this place in life? You know, is this my beautiful house? That song. And so just kind of thinking through the path to where I am today. You know, I'm at Georgia Tech now, but as Luzu alluded, I was actually born and grew up a lot closer to where we sit today. So born in New York City, there I am at Rockefeller Center at the holidays. And then my parents moved to central New Jersey when I was 3, so I did all of my grade school in the West Windsor-Plainsboro school system, which at least at the time was like a big Rutgers feeder. I think we had far more students go to Rutgers than any other college from my graduating class. And actually, I got to spend the summer before my senior year of high school at Rutgers. So in school, I loved all the science classes, but you don't really take engineering classes in grade school. So this program, this is from the current website, so I guess it's still going on, immerses students in engineering for a summer, and I thought it was fantastic. I met people who knew even more digits of pi than me, which I didn't know existed, and I started college as a result as an aerospace engineering major, thinking that this is what I was going to do. So it had a big impact on me. That said, as Luzu noted, I did go to a different New Jersey college ultimately and switched to an astrophysics major in the first year there because the thrill of scientific discovery was really what excited me the most. So really, I spent most of my life in New Jersey, New York, and then the anomaly is sort of like, how did I end up at Georgia Tech? And of course, part of the answer is just when a world-class institution like Rutgers or Georgia Tech offers you a faculty job, you go there. But an interesting, another life event that has happened in recent months is, unfortunately, my mom passed away, and she still lived up here in New Jersey. And so I had a couple trips up here last fall to go through her things, and there was this crocheted family name thing that hung in a frame on our wall in my house growing up for all the time we lived in New Jersey, and so I took this down to pack it and take it down to Georgia with me. And when I took it off the wall, I looked on the back, and the picture frame has this label indicating that this was purchased, framed in Snellville, Georgia, which is about 30 minutes away from Georgia Tech, out of mid-town Atlanta. So I've had my eyes open to, like, my family has this Georgia history, and while it doesn't maybe tell the whole story of how did I get to this, end up as a happy Georgia Tech professor today, this is the kind of thing that I'm going to tell some stories in planetary science about, where you can find clues that maybe sort of help you put together a story of how things ended up the way they are. So to get to the actual science, I'm going to talk first about the campaign to bring back carefully chosen samples from Mars to the Earth, which is very much in the news lately and kind of the big focus of planetary science for NASA this decade and even in previous ones. And that will sort of segue into talking about volcanoes on Mars. And one of the first geologic landforms we ever saw on Mars was a volcano, was a set of very large volcanoes, but we're still discovering new ones all the time, some in kind of important, interesting places. And then you can't really be a well-funded Mars scientist without searching for water on Mars. So I'll talk a little bit about trying to connect the mineralogic evidence for water on Mars to some of the geomorphologic evidence. And then we'll jump to stuff that originated outside the solar system, but actually is making itself available for closer inspection by virtue of these interstellar objects that visit our solar system occasionally. So if you've been wondering what the background here is, this is a scene, an image captured by the Opportunity rover, which landed in Meridiani Planum. As Luzu said, my PhD advisor, Steve Squires, was the PI for the Spirit and Opportunity rovers, so I was following this mission throughout grad school, even though mostly what I was doing was more orbital remote sensing. But Steve would tell you they landed in Meridiani Planum because it was flat as a pancake. This is like the safest place you could find to land and easily traverse on Mars. As far as the eye can see, it's just short height sand ripples, and then these little outcrops of planed down light tone bedrock peeking through. Except in a couple places you see something that stands out, and maybe I'm only showing you this one image so you don't maybe have the context, but seeing a big dark rock protruding from the surface like this was anomalous throughout the Opportunity mission and led people to ask, how did this get here? And the answer, as is often what we resort to for understanding weird things that happen on planets, is impact cratering probably ejected this from the shallow subsurface at some location in the vicinity of where Opportunity was. And this is a good kind of low energy example of the process that also sends rocks all the way from Mars to the Earth in some cases. So large enough impacts can eject things all the way beyond escape velocity. So they go into a heliocentric orbit that through various interactions with other bodies can put them on a collision course with the Earth. And we find them as meteorites in similarly flat and bland places like Antarctica on the Earth, as some current and former members of this department can tell you about. So I said the first thing I was going to talk about is sample return from Mars to the Earth. The first question you might ask is, why do we even need to do that, given that there are pieces of Mars naturally coming back to the Earth? And I love meteorites. They've been incredibly scientifically valuable. So just, this little line up at the top there is not necessarily my opinion. I don't want to offend any meteorite people. I have something else nice to say about meteorites later in the talk. But the consensus of the scientific community is basically the meteorites are, first of all, probably not representative of sort of a randomly chosen set of Martian rocks. There's certain rocks that would survive that impact process and get through the Martian atmosphere and the Earth's atmosphere more easily than others. And they actually are the opposite of maybe the rocks that we'd be most interested in, the kind of softer sedimentary rocks that we might do our astrobiological investigations on are not really going to be, or in practice are represented amongst the meteorites. And we also don't have the context, so we don't know how those rocks came to be, getting back to the question in my title. So the planetary science community, organized by the National Academies, has done 3 so far every decade surveys of the field, and they sort of assess what's been done in the past decade and say what should our priorities be for the next decade. And for every single one of these so far, they say returning samples from Mars is the highest priority investigation in all of planetary science. A decade ago, saying, we need to at least get this started by launching this rover that you see here, the Mars Astrobiology Explorer Cacher mission, which became the Perseverance rover, that could collect samples that then a future mission would rocket up to a Mars orbiter that would then get them back to Earth. It's a multi-stage campaign. And then 2 years ago, the most recent survey came out basically confirming that this is still the community's opinion. We need to get these samples back from Mars. So I say this has been in the news recently because you might have seen there were headlines last week when NASA announced that officially they're going to Congress had kind of given leeway to spend a range of different amounts on Mars sample return this year, and NASA is electing to spend kind of the minimum amount, pushing development forward internally, and instead to ask private companies essentially to come up with ideas for how to do this more cheaply than JPL has said they could do it for, basically. And so the exact timing of when this campaign will be brought to fruition is a little bit up in the air, and actually as we speak, there is a meeting of interested Mars community members discussing what exactly this might mean for the future of the Mars program. So I'll have to read about what they talked about later. But in any case, sample return remains the goal, despite the fact that we can do a whole lot with just sending instrumentation to Mars to orbit it or to the surface. And this, as one example, is a map of the kind of stuff I've contributed to over the past decade and a half, using mostly orbital data to map out different kinds of minerals across the surface. And this map in particular from a review paper is showing detections of hydrated minerals or minerals that form through water-rock interaction, we think, ranging from clay minerals, phyllosilicates, to salts like sulfates, chlorides, carbonates. And you can see they're pretty broadly distributed across Mars. It almost makes me wonder, how are you going to pick just one place to return samples from? When it costs so much to do it from one site, you're only going to get one, and how do you pick where to go? So I think they did the best with that decision that they could, and to actually address the title question of how did these minerals get here, what do they actually mean, how did they form, when, etc., we do need to go a little bit deeper, and potentially sample return is the most, bringing the most potential capabilities to bear to answer that question. So the spot that was chosen is kind of here in this cluster of detections of phyllosilicate minerals, carbonates, even near some sulfate salts and opaline silica in the purple. And that is a place called Jezero Crater. And this shows some of the orbital infrared mapping of minerals with an instrument called CRISM that I've used pretty extensively, and will show some newer results from. But this was a big part of the basis for choosing this landing site, is that you have in especially the sort of cyan colors up here around where a nice sinuous channel enters into this roughly 45 kilometer wide crater. You have in the cyan colors really strong spectral signatures of carbonates, also some clay minerals, and then most of the other colors, yellow, green, also include carbonates and clays. So a basin here that seems to have maybe had water flowing into it based on this channel. where some of these minerals that might record the ancient climate and might have been precipitated at the same time that, if Mars was ever habitable, maybe you could have preserved some evidence for that. That's part of the dream of what you might find with sample return. So that's where this is, again, the first step of the sample return campaign became this Perseverance rover. It landed right about at the tip of the arrow there, and it did that in early 2021, so it's had about 3 years on Mars so far, and I've actually been quite impressed as a veteran of the Curiosity rover mission. We've been on Mars for over a decade and have drilled just a couple dozen drill cores to do the most detailed analysis on. So I sort of thought there's no way within NASA's nominal 2-year mission they're going to get dozens of samples stored for sample return, but the Perseverance team has maintained a pretty fast clip of characterizing the rocks. If they look interesting, put them in a sample tube, and some of these tubes they leave on the surface for some TBD spacecraft to go pick up off the ground. Others they keep on the rover to maybe put them on said TBD spacecraft. Again, how exactly the samples are getting back is still not really decided, but samples are being collected from the site on Mars that might one day come back to Earth. So what are they? And really the very first from the very first rock that they looked at in detail, so there's an abrasion tool where they can grind off, first of all, remove any dust and then grind through any superficial weathering rinds on the rocks. And the very first rock that the rover did that on had quite a surprising texture, I would say. So it kind of looks pixelated here, but you can see that at this resolution here, your eye can pick out individual grains. They're not like well-rounded sedimentary grains. They're sort of interlocking grains at about the millimeter scale. And, at that millimeter scale is macroscopic. To see macroscopic crystalline grains within a rock suggests a long time scale of cooling from a formerly molten state. And so basically seem to imply that either this is an intrusive igneous rock crystallized underground, or maybe the consensus now is more likely that it is part of a thick lava flow, and the deeper part where if you had lava flowing out at the surface, the upper surface of it could have cooled quickly, formed finer crystals or glasses, but deeper within it you could have formed this somewhat coarser grained material. But it was surprising. This was a continuing a long history of we go to Mars to try to find sedimentary rocks, evidence for water, and instead we find volcanic rocks that, there'd been remote sensing that suggested there might be some volcanic rocks in the crater, but nobody really predicted coarse, I don't know if you'd call this coarse, but coarse enough to see crystalline igneous textures in a number of the early rocks drilled by the rover. So, I like doing observational science because, again, the thrill of seeing something totally unexpected like this is fantastic. But to really understand it scientifically, you then have to ask the question, how did this actually get here? So where did all these volcanic rocks in the crater come from? And to try to answer that question, let's take a step back up out of Jezero crater and look down on it from orbit. Maybe I'll ask you all, if you just look, so this is topography of the crater. Again, it's this 45 kilometer wide, roughly circular thing here. Does anything strike you about the crater that, is different from just it's not just a hole in the ground here, there's something else going on nearby? What? Yeah, so there are 2 river channels coming in at upper left, and that is where they wanted to land the rover to look at what have been interpreted as deltaic deposits. Those channels in, and then this additional channel that goes downstream away from the crater, sort of got all the attention prior to landing, because the outlet channel in particular is valuable because it suggests that not only did water flow into this crater, but it filled it to the point that there was an overflow and you eroded a channel into the rim. But yes, I heard other people saying, what's the thing at the lower right? And the very first time I looked at Jezero crater in grad school with remote sensing data, I was like, huh, cool crater. What's this giant mountain with a crater on the summit of it that's right next to the crater? Is anybody looking at that? So if nobody had said that, then this would have been my additional hint. This is a maybe 2 or 3 times vertically exaggerated oblique view from the north of the crater. You can see the channel flowing in here and the outlet channel here. And the crater has a raised rim that's sort of variable degrees of preservation as you go around it, but this feature here on the southeast side of it stands out topographically as well as in the thermal data. So the colors here are nighttime infrared brightness, basically corresponds to temperature. And so this mountain, as well as kind of the fine-grained materials filling the bottoms of these channels, is getting colder at night. It's cooling down more rapidly, meaning we would say it has a lower thermal inertia, lower resistance to temperature change, cools down a lot overnight than the surrounding plains on Mars. And that generally corresponds to things like grain size, so maybe a fine-grained material at the surface of whatever this is. And here's an even more suggestive view, just looking again at the topography, zooming in on this feature, which we worked with the USGS and the International Astronomical Union to get it officially named Jezero Mons, because that's what it is, a mountain next to Jezero crater. It's about 1.5 kilometers, I think, in total prominence above the surrounding terrain. And again, I got interested in this when I saw it in low-resolution orbital data like a decade and a half ago, but all of the orbital resources were being focused on the areas on the other side of the crater with the cool channel. So it's actually only recently that we've gotten good data sets to try to understand this feature a little bit better. That said, you could see it from the very first images taken by Perseverance. There on the southeast horizon. It's, again, the whole crater width away, basically 50-ish kilometers. And so Perseverance took this picture in its first months on Mars, and this is about the best view we're ever going to get of this feature from the surface, because they're driving Perseverance in the other direction toward the deltaic deposit and eventually out of the crater. So this is a nice kind of elevation profile of whatever this mountain is, but again, from orbit, we actually can do roughly an order of magnitude better in spatial resolution with the cameras that we have there. So I'm going to show you some of what we see there. So this is actually, the colors here are from that CRISM instrument I mentioned before, an imaging spectrometer that takes a visible and shortwave infrared spectrum at each point across a roughly 10 by 10 kilometer scene, and you can take a few of these and then design parameters that will track the presence and maybe related to the abundance of certain minerals. And so you see a lot of green here. Those are pyroxene minerals. That's one of the easy things to detect, which you would expect to be a significant component of any basaltic volcanic material. There's pyroxenes lots of places on Mars, of course. One point about this is just if you kind of look at this top-down view, planform view of the feature, I think it looks, to me, strikingly similar to a number of stratovolcanoes on Earth, and in particular, there's this one in Antarctica that I have seen cited as a potential analog for some other recently identified possible volcanoes on Mars, and even more in this case, I think there's a resemblance in the sort of not circular but line segmented outline of things. You got maybe a sector collapse feature in both cases. So you always want to be a little careful just saying this thing looks like this and thus is the same, but they do kind of look like each other. But then, yeah, in terms of the mineral mapping, you also have some secondary minerals, phyllosilicates, maybe some carbonates, which again are widespread throughout Jezero crater and actually the surrounding terrain. And some of what we see on Jezero Mons itself is likely just craters have penetrated through whatever the mountain is made of and revealed that subsurface widespread altered unit. But if we look in particular at sort of the margins of this Jezero Mons feature, where it extends out onto the surrounding plains on the right, this is kind of just outside the Jezero crater rim, and then this smaller box is just within the crater rim. Here's what it looks like. You can see a well-defined margin where you go from the kind of pyroxene dominated in terms of the spectral signature and bluish in enhanced visible colors material that we would map as part of Jezero Mons versus the more widespread older unit that seems to be stratigraphically underlying that. And so that's just outside the Jezero crater rim. This is actually on the eastern floor of Jezero crater. You have, I don't know, you could interpret these as some kind of flow front coming down off the mountain into the crater. If so, it's certainly eroded at the edges by all the little sand ripples that you can see here. But evidence that materials from this mountain were transported somehow into at least some parts of Jezero crater. Maybe that's a lot of caveats, but so to like assess, is this most likely a volcano or some other type of feature? We first tried to find, are there similarly sized and similar in other ways features elsewhere on Mars that people have interpreted as volcanoes? And a lot of the Martian volcanoes are shield volcanoes. And the originally discovered ones going back to the early missions in the 70s that have names are mostly pretty big compared to the Jezero Mons feature. But here's one that is like a factor of 3 larger that we put into a comparative analysis that we did. And then we tried to find examples of potential stratovolcanoes, which we thought might be a better analog. And so here's 2 identified a couple decades ago in a region called Aeolus on Mars that are similar in size, shape, and also have the comparatively low thermal inertia, meaning maybe fine particle sizes that these authors interpreted as consistent with ash dominated surface materials. And then here's one other example from a couple years ago of some little knobs just south of the Valles Marineris Canyon system that are also low thermal inertia and show some clay spectral signatures. So we thought this could be a good analog because we see some of that around the summit crater of Jezero Mons as well. So a couple summers ago, I had a fantastic REU student, Sarah, basically measure morphometric parameters for Jezero Mons compared to some of these other hypothesized stratovolcanoes on Mars, one shield volcano, and then the Mount Sidley example from Antarctica. The thermal inertia, again, you can see pretty comparable, around 200 is sort of, if that's a single type of surface material, it would correspond to a fine sand particle size, but also could be something even finer grained mixed with some solid rock to give you an average fine sand size particle is what the thermal inertia kind of corresponds to. You can see the Aeolus region features are about the same size as Jezero Mons diameter-wise and height-wise, and then if you in particular look at like the height to diameter ratio for these 3 and Mount Sidley, basically identical, and the size of the summit crater compared to the size of the feature as a whole are also comparable. So none of this proves that it is a stratovolcano, but what we thought we would do is sort of make a truth table where we try to put our various observations and compare them against the set of ways we could think of that you could get a hill with a crater on top of it. And so one, the sort of null hypothesis is this is just an old mountain, a highland high-standing feature that happens to have an impact crater on the summit. If that were the case, then I don't know why the thermal inertia would be different from much of the surrounding terrain. Also, if you count impact craters on this Jezero Mons feature, you infer a younger age, or at least lesser crater retention than the surrounding plains. So that doesn't quite fit with this, this null hypothesis. You can also get pedestal craters where the formation of the crater kind of, and its ejecta, armors the surrounding surface against erosion. So you get a crater kind of sitting up on a platform or a pedestal, but the shape of those, if you took a profile across it, doesn't really match the smooth, continuous slopes that we see for Jezero Mons. And if anything, if you've armored the surface, you should probably see a higher thermal inertia, not a lower thermal inertia. If it were a pedestal crater. There are also sedimentary volcanoes, so mud volcanoes is what you hear about most often in the Earth context, perhaps. But at least on Earth, these are only up to like an over an order of magnitude smaller than Jezero Mons. So this would be a heck of a mud volcano if that's what it is. If it's an igneous volcano, just kind of putting these two sort of end members in there, again, the low thermal inertia and maybe ease of alterability to form secondary minerals like clays are not things you would expect for a shield volcano, but are at least consistent with a stratovolcano. And so we have this paper in review now suggesting that that is what Jezero Mons most likely is. And, it's then a further leap of reasoning to say, well, that is where the samples of volcanic rocks that Perseverance has encountered must have come from. We definitely don't have proof of that. But so there's the coarse crystalline rocks that I showed. They also saw some evidence for things that almost looked sedimentary, but the consensus rover team interpretation has been that they're probably ash deposits, pyroclastics. And if you just ask, what is the nearest source of potential pyroclasts that is visually evident at this site? I think the answer to that would be Jezero Mons. So that was one little project that we did that fits under the theme that I said I'd kind of segue into of previously missed Martian volcanoes, but it's one that made me worry if we, this is a place where we are investing the major campaign of planetary science for the next decade, and there's arguably a volcano there that nobody noticed when we were considering it as a landing site. Like, how many more old, maybe more degraded volcanoes across the surface of Mars have we not recognized to date? And I'm not the only person who has worried about this or wondered about it. And in particular, an even larger set of potential volcanic constructs was pointed out about a decade ago in this paper in Nature that was looking at a region in Arabia Terra, this heavily cratered region of Mars, kind of north of where the Opportunity rover landed, where, if you look at the image here, you can see lots of nearly circular depressions, and whenever we see a nearly circular depression on a planet's surface, we sort of immediately assume it's an impact crater. So that had been kind of the tacit assumption for basically everything you see here. And what Michalski and Bleacher pointed out is some of these things really are not that circular, and they in some cases lack raised rims like craters should have, and they have kind of weird structural features within them. And could they be volcanoes instead is the question they asked. And in particular, could they be calderas of super volcanoes? Maybe the analogy here is to something like in what you have at Yellowstone. So this paper came out, again, about a decade ago, and then there was a follow-up just after we'd finished looking at Jezero Mons that was associated with this NASA press release, thousands of ancient super eruptions on Mars. And here's the paper in GRL. And in particular, what they were doing was a combination of modeling. If you had a pyroclastic eruption from the little red spot here is Eden Patera. That was kind of the maybe most robust candidate to be a volcanic caldera in this region. if you had an eruption there and then modeled for various assumptions of atmospheric density and wind patterns, what distribution of ash as a function of distance and direction from that source would you expect? And they then compared that to measurements of thicknesses of layers that I guess they thought could be consistent with ash deposits. And then what kind of got my attention even more was they connected it to the mineralogy and said that where they saw minerals that they said would be consistent with altered volcanic ash, and this is things like hydrated silica, clays, sulfates, kind of a lot of the things I showed you on that map of global hydrated minerals on Mars, they were arguing at least could be consistent with altered ash, but they were then claiming that across a pretty wide swath of Mars, you see the longitude lines here, this is like a quarter the width of all of Mars, that maybe every example of these types of minerals in that zone could be explained as altered ash from these few volcanic calderas on the west end there. So I thought maybe, but maybe, yeah, so just to show you on the global map here, it would be kind of all of this, which does incidentally extend all the way east to where Jezero crater is, where the Perseverance rover there is there today. So yeah, is again asking, is this really how all of this got here? So what I had another student look into is, can we find evidence for these minerals and the types of deposits they were mapping thicknesses of closer to Eden Patera itself? I think their closest point that they were interpreting as a potential altered ash from here was somewhere off the map up and to the right here. So I had this fantastic undergrad, Grace, she's now a first-year grad student at MIT, looking for what minerals were present in essentially all the CRISM observations, especially focusing on the kind of weird-looking depressions throughout this region. And all of the dots here are places where she found hydrated silica, one of the things that can be associated with volcanic products, though certainly not exclusively. But importantly, she found a detection of this within the caldera of Eden Patera itself. So that's what I was kind of going for with this project, is if across 90 degrees longitude of Mars, all of this has come from this one source, then we should find even more of it. It should be easy to identify right around the source itself. And so yeah, within Eden Patera, and then I'll show you this site here. It's an unnamed crater that we'll just call Site B. And here's a CRISM mineral map. Again, you can see it's like a nearly circular depression, but without much of a raised rim, and kind of this weird terrace inside, and some like maybe structural collapse features around here. Grace saw a lot of the same minerals that we saw on Jezero Mons, may not be particularly diagnostic, but pyroxenes, and then especially around the edges, things like silica and a little bit of clay and phyllosilicate. And we've been targeting this now with high-resolution imaging, and so this area that has some silica-rich materials. The upper right of the depression here, you can see in a nice color image from the Cassis camera I work on the ESA trace gas orbiter. And I'm really not a volcanologist nor much of a geomorphologist either, so I would love to work with somebody who knows more about volcanology, about like what should we be looking for and how do we interpret morphologies like this. But sadly, the CRISM instrument required cooling of its infrared detector in Mars orbit to get good data, and the coolers have now been exhausted, so we are not getting any more CRISM compositional information, but we can still take high-resolution images, and as we continue to target more kind of weird-looking depressions in northern Arabia Terra, we see a lot of light-toned, maybe layered deposits throughout crater floors that one could interpret as consistent with altered ash. if one wanted to. Again, at the end of the talk, or if you talk to me afterward, feel free to poke holes in any of this, because sort of everything I'm presenting today is stuff that is not quite published or just published, so it's probably very holy, and feel free to give me your thoughts on anything. But one other thing that I encouraged Grace to do in this North Arabia Terra region, because she found all these examples of hydrated silica, is there have been a few papers in recent years showing that is a phase that the spectrum can reveal potentially a lot about how it formed. And so basically the exact positions of the absorptions in the infrared spectrum, their relative strengths, even the concavity or convexity, the shape of these absorptions. If you plot examples from the Earth, those properties, where things plot in this parameter space, tells you, is it more amorphous or more crystalline opal? Things that formed in lower temperature weathering versus hydrothermal environments separate out. And for Mars, too, there seems to be a correlation between the setting, where you can find different silicas across different sites on Mars, versus the spectral properties. And so maybe we can use the details of the spectrum to figure out how things got there, is the hope. So here's a giant table from Grace's paper that she is soon to submit, and just to call your attention to a couple particular things. So low thermal inertias, again, at most of the sites where she found this silica, with an interesting trend that kind of the farther away you get from the putative sources, you maybe get finer grains, as you would expect from what grains could be dispersed more distantly in the atmosphere. That site B that I showed you, that's kind of the nearest one to Eden Patera, had spectral properties consistent with hydrothermalism. And then comparing to silica at other sites on Mars that are either volcanic or other types of environments, we had a lot of matches to volcanic sites in this study, and that's different from what we saw in a few other studies that I'll briefly go through, looking at similar things with silica spectroscopy. So one risk with doing these large regional studies is that maybe you're lumping things together that are really distinct from each other, and in particular, the sort of two most northerly silica detections in Grace's study region here are kind of down at a lower elevation, and you can see there's sort of a texture of scattered knobs up here. Looks a little bit different from the cratered landscape down here. And a colleague in Mars Science, John Carter, a fellow spectroscopist, had this LPSC abstract 2 years ago saying that some of these knobs, which others have interpreted as mud volcanoes, the sedimentary volcanic constructs I alluded to before, have silica associated with them. And so these could be examples of where you have a more water-rich environment during the formation of silica, perhaps. So it's more of a tie between maybe not a fluvial landform, but a sedimentary, low-temperature sedimentary landform and an aqueous mineral. So I have just a couple quick hits that also fall in that theme from other studies. One looking at the Eridania Basin in the southern highlands of Mars, which I'll say we were in part motivated to look more closely at spectroscopically, thanks to some work by Dr. Oja here. And I love this paper of Luju's, basically proposing a source for the hydrothermal system that others had suggested might have powered at least the production of a lot of hydrated minerals throughout this region, and it's been argued geomorphically that maybe they're up to the black, or at least the white contours here could have been large standing bodies of water. You'd call it a sea, I think, if it was this whole black contour rather than a lake at some point in the distant past here. So my PhD student, Emmy, went looking at specifically silica exposures that we'd known from previously published work occurred in a few places throughout this region, and applying those, like, is it hydrothermal or weathering, and what kind of opal spectroscopic distinction tools that I showed for North Arabia Terra. And you can see, anything that would be outlined in purple would be hydrothermal. There's only one that fell in that category. So in the paper that Emmy just submitted, we basically said the amorphous silica in this basin is probably more consistent with low to minimal water to rock, low temperature aqueous processes, but with potentially at least one exception, and there's a lot of other mineralogic, diversity of aqueous minerals, maybe some high temperature phases specifically throughout this basin. So I don't think Lucy was wrong that there has been hydrothermalism here just because of the silica. I want to quickly talk about this sort of broader goal of tying fluvial geomorphology to the mineralogy of water-rock interactions on Mars. And you'd think, like we've known about channels, valley networks on Mars as evidence for surface water flow since Viking, and we've been mapping aqueous minerals from orbit for 2 decades now. But surprisingly, these are less correlated than you might think. They're both evidence for water rock interactions perhaps in the past on Mars, but from the very first sort of seminal paper mapping out aqueous minerals, it was noted that they don't really seem to be correlated with each other spatially. And there was this abstract at LPSC a few years ago that quantified this and showed that the distribution of morphologic valley networks in red versus that of hydrated mineral detections across Mars, like the other map I showed you, are actually they overlap with each other less than either of them does with a set of randomly chosen points on Mars. In other words, they're somewhat anti-correlated. And it's a global trend. There's obviously counterexamples at smaller scales, but it's sort of suggested to them that maybe a lot of the formation of the aqueous minerals happened in the subsurface if the surface water environments were not ones that seem to have deposited a lot of aqueous minerals. So NASA's always eager to find counterexamples to this, because really when we send a multi-billion-dollar spacecraft to the surface, we'd like there to be both morphologic and mineralogic evidence for water there. And so I got, back in graduate school, excited about this one site along a Martian flood channel called Shalbatana Vallis, where this paper came out while I was in grad school. They mapped what they interpreted as a Gilbert-type delta in sort of a localized depression along this flood channel, and then there were these light-tone sedimentary deposits on the floor of the channel that, again, back in grad school, I reported there were salts and clay minerals there, and have never gotten around to publishing it. But we just recently got some nice imaging of this with the Cassis color camera. Here's this basin that has the aqueous minerals within a clearly fluvial setting, and if you look along Shalbatana Vallis more broadly, you can see some other outcrops that look similar. And then zooming out, Shalbatana Vallis is one of several channels that empty into this large impact basin called Chryse, where NASA has actually landed twice with the idea that we could find sediments carried down streams like this into this large sedimentary basin. And of course, both of these mainly found volcanic rocks, like I said before with Perseverance. That's what happens to a lot of NASA missions. But basically what we've been working on is suggesting that the logic was sound, and that if you just go to the right places, you can find at least localized areas where aqueous mineralization arguably associated with the fluvial events that carved these channels. This is a place near the mouth of Cassis Vallis where silica was found in a kilometer scale outcrop, and then another one at this other outflow channel halfway between the two here. So we're kind of mapping out more of these. I had two current and previous undergrad at Georgia Tech helping me with this, and this is like my main paper that I am going to try to get some progress made on this summer. I think I'll skip over this in the interest of time, but just the point was that even without spectroscopy from CRISM, with just a few bands from color imagery, you can maybe make some mineralogic distinctions as well, but you can ask me about that afterward if you want. So I want to spend the final few minutes talking about interstellar objects, because Luju asked me to. You might ask, how did I, a Mars scientist, get here to looking at these? I will say that part of it is inspired by Luzu's own scientific trajectory. You know, in undergrad and then in grad school, he reached some significant scientific highs, and instead of resting on his laurels or even continuing to do the same kind of science, he's broadened to a tremendous array of different tools for Mars science, and now studying Kuiper Belt objects and exoplanets. You know, if he can do all of that pre-tenure, then surely I, safely tenured, can branch out as well and explore some different topics. And I think this is a timely one because although there's only 2 interstellar objects we've confirmed to date, and I'll show you briefly what we know about each of those, there's this new observatory and survey that are going to be starting next year that this is a very optimistic estimate. It's kind of the highest number I can find in peer-reviewed literature, but probably at least 1 per year-ish. We should expect new objects in this category to be found once the survey turns on next year. So it's an exciting time to be getting into these kind of studies. And as I said at the beginning, I was an astrophysics major. I sort of brought spectroscopy with me from that to Mars geology, but you know, doing remote sensing is kind of how I got my start, and is what I've been doing, and is what we're going to have to, at least for the time being, do with these interstellar objects. So I think I'll skip this too. So the first evidence that these were, the first example of these objects came, what is this now, a little over 6 years ago, late 2017. There was this object identified with a survey telescope, Pan-STARRS, in Hawaii. So a lot of the authors here from University of Hawaii, led by Karen Meach, that saw an object moving quickly across their survey fields, and if you trace back where it came from, it's from well out of the plane of the major planets in the solar system and at a high enough incoming velocity that it clearly originated somewhere outside of our solar system before actually passing closer to the sun than Mercury, and then pretty close by the Earth that allowed us to see it, and then heading on its merry way back out of our solar system. So we had a very brief window of time when observations could be taken of this object while it was near the Earth. It had the colors of a comet, so the black dots are the measurements from this object named Oumuamua. And then these are comet spectra, and D-type asteroids are asteroids are not active like comets, but D-types are the ones that are more predominant in the outer solar system beyond the main belt. So it kind of looked like an outer solar system type object in that sense. It also, so this is not Oumuamua, this is the comet that the Rosetta mission studied. You could see this jet that, you know, like a rocket, is going to redirect the orbit of this comet to a certain degree from just what gravity would do. And there was evidence that Oumuamua was also moving in not just a gravity-driven way. However, there was no obvious dust carried into a coma around Oumuamua, nor any detections of CO2, carbon monoxide, water, the typical gases that comets generate. What was detected was some extreme brightness variations. So this is the brightness as a function of time over just a few nights of measurements. The scale for the non-astronomers is basically such that this is like an order of magnitude plus difference from the brightest it looked to the faintest it looked. And in particular, you have these kind of sharp troughs and broad peaks, and that's diagnostic of a rotating, highly non-spherical object, more so than something that just has brightness variations on its surface. So the really extreme brightness variations in this combination of properties led to some dramatic speculation in the media and even in the peer-reviewed literature a little bit. I don't think that's the first hypothesis that I would go to, but assuming that it is a natural object, it's still a pretty weird one by solar system standards. The extremeness of the axis ratio you would need to generate this kind of brightness variation by rotation would mean it's either a really flat object or an elongated, cigar-like is a term that was used which we don't have a lot of things that look like this in our solar system. You can also see that this curve isn't quite periodic, and that's because it's in a chaotic tumbling rotation state that might relate to how it was ejected from wherever it formed in the first place. Less than 2 years later, we got a second data point, and so far, sadly, this is the only other one we have, but it looked quite different. Borisov was the astronomer who discovered this one, which is clearly cometary, was again on a high velocity trajectory indicating origin outside the solar system. And when this picture was taken, the press was like, oh, well, this one's just a normal comet. No, it's not a normal comet, so that there's different chemical, molecular abundances you could plot, but for this one in particular, here's all the solar system comets for which we've measured this ratio. Here's Borisov. There's one, I guess, probably solar system comet that has an even higher value of this ratio, but the interstellar object is in a no man's land of composition, so clearly not like a typical solar system comet. It was easy to detect over a broader span of time because it had this bright halo coma around it, but that actually made it more difficult to characterize the state of the solid nucleus that must be at the center of all this. However, there are more observations of this body than have been analyzed in detail or published on to date, and so what I've recently started to actually work on this topic is collaborating with Karen Meach, who has Hubble data on Borisov, showing things like if you stretch the image, particular jets of outgassing from the surface, that if you track how those rotate, maybe that could give you a rotation period. And if you wait until it's far enough away from the sun again, then maybe its activity diminishes enough that you could see the nucleus. This is our hope. And getting a firmer number for the size of Borisov would really help to pin down, we only have 2 data points to construct the properties of the population for now. And so that stay tuned, maybe later this year we'll have some results for some of these things. To just briefly say, how did these get here? Going back to my title question, there's a whole range of hypotheses that could explain things like the elongation or the flattening that I won't go through in detail, but sort of any of these would have distinct implications for what we would observe. And I guess worth acknowledging that we, at least for the first 2, were not able to figure out where they came from precisely, but I think that's okay because we don't know that for meteorites. And like I said earlier on, meteorites are still really valuable. They're samples of a process that we otherwise wouldn't get to see. So what I really want to see happen, and I'm not the only one saying this, but would like to see a mission to one of these objects in the coming years where just an image of the actual shape and size of the nucleus plus some chemical measurements would resolve amongst a bunch of those different hypotheses that have been put forward. It would be a challenging mission in the sense that you would probably have a really high relative velocity between spacecraft and the object. However, when I was still, the little kid living in New York City, ESA did this with Comet Halley and showed us what a comet nucleus looked like for the first time. I'd like to think we could do it again now. The additional challenge we didn't have with Halley is that we wouldn't know until an interstellar object was already here where we were going to go, which is not how NASA typically plans missions. They want to know the target. But ESA is developing currently a mission that will launch, wait in space until an Oort cloud comet, in that case, is discovered, and then divert to that. Just one final word about the interstellar objects is I don't think it's surprising that they're here. In fact, here's a paper from the 80s saying, why haven't we found any interstellar objects? We'd expect some material to be ejected from other systems and make its way to the solar system. It's the properties of the first few. The fact that Oumuamua and Borisov were so weird, to me, is reminiscent of the first exoplanets we found, which of course we thought other stars probably had planets too. But then the first ones we found were Jupiter-sized planets, orbiting way closer to their stars than we thought planets could ever form. And indeed, probably they can't form there, but they can move after they form. And now that's an essential part of how we think about how our own solar system formed. So to me, these objects have the potential to, again, revolutionize how we think about planet formation in general. So I can't wait until we get a third and fourth and so on. So given the hour, I think I will just put these conclusions up there, and happy to talk about any of these things further if people are interested. Thank you.
Questions for James? Students first.
Yeah.
You alluded to there being like a regional behavior in some of the calderas. Is that the case? Is there more to that?
So let's see if I can go back. The North Arabia Terra region, there are a number of them that all have this kind of weird crater shape to them. So Eden Patera was the sort of one that got the most attention, but there's other kind of weirdly, nearly circular, but weirdly structured internally depressions. And I think even farther east of this, there's some more examples. So this is like, 1,000+ kilometer wide zone that has these large calderas. In the place I talked about before that, around Jezero crater, where Perseverance is, go back to the topographic map I showed you all. So this is, to me, the most obvious feature within a few hundred kilometers that, like, has a crater up at the summit of it. But there are, again, within a few hundred kilometers of Jezero, other isolated topographic rises that could be more degraded versions of this. And it's probably not visible in this. Yeah, okay, so you're actually in this whole region on kind of the northeast flank of the Syrtis Major volcanic shield. So I should admit, therefore, that there are other volcanoes in the area besides this putative one that we identified, which is, as you'd expect to see that in a volcanic province. We just highlighted that one because it's the closest to the crater itself. Yeah.
Thanks for the very talk. You showed the table whether you can, with different parameters, whether you can call just a moment. I was just wondering if you could range all these parameters as saying yes and no, and like risk analysis, make them.
Yeah, the way we did this was very qualitative, like red X bad, black check mark good, just make a visual. But yeah, that maybe would be more convincing to do it in a more standardized way. Yeah. Some of them we didn't really know, like, a volcano doesn't have to have clay minerals, but a fine-grained pyroclastic dominated volcanic construct would be more likely to have them than a shield volcano. So question mark. So.
Which of these parameters is more performance?
That's a good question. I'm open to perspectives from volcanologists on what evidence you would take more seriously than other things, but yeah.
Okay, well, it's 6 minutes past
Yep.
time, so yeah, if there's no other questions, thanks, James. And,
Thank you.